And hello everyone here. So today for our speaker, we have Albert Jiang from Mistral AI, and also from the University of Cambridge. Nice to meet you, and thank you for coming today and being our speaker. So Albert is a AI scientist at Mistral AI and a final year PhD student at the Computer Science Department of Cambridge University. He works on language model pre-training and reasoning at Mistral AI and language models for mathematics at Cambridge. So thank you for coming today. And today Albert is going to talk about Mistral, a sparse mixture of experts language models. And yeah, I think I will now leave it for Albert.
Hi, Emily. Thanks for the really nice introduction. So let me share my screen here. Thanks very much again for the really nice introduction, Emily. So today I'll be talking about demystifying mixture of experts. And my name is Albert. I'm a scientist at Mistral AI and a PhD student at University of Cambridge. So the content you'll be hearing today. First, I will talk about the architecture of first the dense transformers architecture, just to review, and also the sparse mixture of experts, or SMoEs. So after that, I'll be talking about interpreting sparse mixture of experts models, and the majority of this slides will be based on the mixture of experts paper that we put out earlier this year in January. And throughout this talk, if you have any questions, feel free to raise your hand, and I'll be really happy to answer. And also, I'll be posing some open research questions because these things are really very much under research, and we hope that more research can be done on it so the open source community can really enjoy the benefits. Okay, let's get started. So first, let's talk about architecture. We can first talk about the dense transformer architecture that a lot of people must have already talked about. But here I want to focus on the Mistral 7B model, which is a dense transformer. The main difference between the Mistral 7B model and the rest of the dense transformer models is that it has group query attention, which is different from the multi-head and multi-query attention, somewhat in between. So for multi-head attention, you have the same number of the same number of keys, queries, and values. And for multi-query attention, you have a lot of queries and just one key and one value. And group query attention are sort of in between, and you have a lot of queries, much less keys and values. Also, there's another difference in the attention we're using for Mistral 7B. That is, we're using a sliding window attention. The idea being for some of the lower layers of the transformer, the tokens, for each token position, they attend to a relatively short span of previous tokens. And as you go deeper in the transformer, the later token positions will get information transmitted from the earlier token positions. And neither of these architectural designs are new. So these are already present in previous works from 2023, 2019, and 2020. So these are really nothing new, but we decided to adopt these architectural changes in Mistral 7B to make a better model. Okay, so after writing these slides, I realized there's actually a huge number of decision choices you have to make in designing a transformer architecture, because there are so many details. So like just presenting this doesn't feel sufficient. So I tried to, first, these are the sort of standard configurations for Mistral 7B. And also I just want to have a very some very clean code in PyTorch that just tells you how to write a single transformer layer. And I'll be adopting the Noam Shazier notation by annotating the dimensions of every tensor as a suffix in the variable name. So let's say our sequence size is 8,000, 8K, and that we have 32 query heads and 8 K and V heads. So this is quite standard for group query attention. And our head dimensions are 128, and our latent dimensions is 14K. So in order to write a single transformer layer, first you initialize your query, key, and value matrices. So here I wrote down their dimensions here, and notice that we don't use bias. So there's no bias in any of these matrices. And we also write down our output matrix. So to know that the output matrix has the same dimensions as the transpose of the query matrix. So in order to write an attention forward layer, so here let's assume that our input X has the dimension L times D. So L is the sequence length and D is the latent dimension. So you first want to use these matrices to try to find what your query key and values are. So here their dimensions have been normalized to L and H, LKH, and LVH respectively. And then you want to apply rotary embedding to your keys and queries. You don't really apply that to values. And then you do a very standard attention mechanism with the queries, keys, and values. To note here, we actually repeat the keys and values a couple of times to make their dimensions match with the queries. And then we just return the output multiplied with the output matrix. So this is your very standard attention forward layer. And to have a transformer layer, you also want to tie that. You want to first do a normalization. Here we use RMS norm over the input, and then we do attention forward. And then we do an attention residual layer, followed by normalization plus an MLP plus a dense residual layer. So this is what's present in a transformer layer. Okay, so with these architecture designs, we managed to make a model that's quite good. So this was released in September last year, and it was able to beat a lot of the Llama 2 models back then, despite being very, very small. Okay, so let's now go to the interesting bits. That's Mixture of Experts. And Mixture of Experts is not a very new idea. It's been present forever. And there are a couple of very quite recent papers that really highlighted the importance and like how what are the benefits you're getting from these mixtures of experts layer models. So I guess probably the most well-known one is the switch transformers. That is the Google paper that scales transformers to trillion parameter models with simple and efficient sparsity. And they discuss a lot about the sort of parallelism decisions you can make about data parallelism, model parallelism, and expert parallelism. And for the mixture of experts layer, it's also it's an even older idea, so from 2017, also by some quite famous people from Google. And the idea is that you try to take out so at the time they were still using recurrent language models. So at the time, the idea is that you try to have a gating layer, a gating network that decides which experts you should route to. Okay, so in our mixture of experts, in our implementation of the mixture of experts layer, we're doing something very similar. So we have the inputs that get sent to a router, and the router assign the gating weights and to pick the top two experts to give these inputs to, and after these experts individually process the inputs, the gating weights will be applied to the output of the experts, and they get summed to get to the results. So if you write it in very mathematically, you can say that the input is X, and the router has a matrix multiplied to it, and then you take the top K experts out of that, do a softmax, and these are your gating weights, and output of the mixture of expert layer Y is the softmax of the top two gating weights times the sweet glue function over X. So for each of the experts. Okay, so a sparse mixture of experts model is quite near the cost performance Pareto frontier, because for each token, the token doesn't have to go through the entire neural network's parameters. Instead, it can just go to like the active parameters for that token, and this mixture of experts model can outperform Llama 2 70B with about 5 times faster inference. So we kind of see it as a drop-in replacement for GPT 3.5, which can also master quite a few European languages in addition to English, and it can gracefully handle context 32K tokens. So this mixture of experts model was released under Apache 2.0, so you can free to use for commercial purposes. Also attach the configurations for the mixture of experts model here, but so you can refer this back to the Mistral 7B to see the differences. Okay, so I want to talk about what does SMoE, which is a verb I just created, the MLP layers actually give you. So the conventional wisdom is that the MLPs in a transformer network store knowledge, and the attention stores algorithms or reasoning, or they sort of implement algorithms and reasoning. So by SMoEifying the MLP layers, we're supposed to get a boost in knowledge, right? And indeed, we try to benchmark Mixtral A times 7B with a Mistral 7B and a couple of Llama 2 a couple of the Llama 2 models, and in a couple of different categories, you can definitely see that on the knowledge-heavy tasks such as MMLU and knowledge, the Mixtral A times 7B model, which is shaded in yellow here, is doing a lot better than Mistral 7B. And on some of the reasoning comprehension and tasks, it seems to be doing a little bit better, but still not as much as it does on knowledge and MMLU. Okay, and here is a different graph where here what we're trying to show is that what is on the horizontal axis is the number of active parameters, and on the vertical axis is the performance of the models on various tasks. And the sort of brown dots here are Llama 2 models, the series of Llama 2 models, and the orange dots are Mistral models from Mistral 7B to Mixtral A times 7B. So the Mixtral A times 7B uses only 12.9 billion active parameters, so close to 13 billion, yet it can perform quite a bit better, especially in the knowledge category. You can see the drop. You can see the increase from Mistral 7B to Mixtral A times 7B is quite huge here. There are some improvements on other categories, but the knowledge improvement is really great. Okay, so there's a research question that is if making your language model, making the MLP layers of your language model can give you a huge boost in knowledge, like how about SMoEifying the attention layers, right? So this is also very, well, not very old, but like quite old idea from 2022 in the switch transformer papers. So the idea is you can replace the trainable QKV matrices with switch layers. So instead of doing a standard matrix modification, you can do a SMoE. So you have a gating layer and then some dense layers for the QKV matrices. And the problem at the time was with stability. So if you use BF16 precision to train your models, they can sometimes diverge. But if you use FP32, they don't, and you get some performance boost, which is nice. But at present days, mostly we're training with BF16, so we have to find a way to make it work. So in order to make this work, maybe you can try better stability techniques, maybe some normalization, or maybe you could use a different way to SMoEify the attention layers. So this is an open research question. I would really like to see some research to be done here. And after this, I want to just talk about several myths that seems to be present around the mixture of experts models. So the myth one is that there are 8 experts in Mixtral A times 7B. So this is partly our fault by naming our model Mixtral A times 7B. So the truth is that every transformer layer has 8 experts, and these experts are permutationally equivalent. So you because the way it works is that the gating network decides how much weights to give to each of the experts, and only picks the top 2. So it doesn't matter. So it doesn't matter how you. So it doesn't matter how you permute them. They will give you the same result. So that means instead of 8 experts, you actually have 32 times 8 experts in total, and they're relatively independent across layers. The miss2 is that there are 56 billion parameters in Mixtral A times 7b, but the gating and the attention layers are shared. So these are not in the A times part. And in fact, there are only 46 times 7 billion parameters in total. And each token will actually only see 12.9 billion active parameters instead of 14. Okay. So another thing that seems to be quite popular these days is to compare everything, tying everything that's related to cost with the number of active parameters as if they're proportional. And that's not quite true, right? Because Mixtral A times 7b has fewer active parameters than Llama 2 13b. But having this sort of expert routing means that you need to send tokens around to different experts, like quite dynamically. So that means you have more communication cost. You cannot just pre-program like which token will be sent to which expert. While you gain much more in performance divided by cost, the absolute cost is not proportional to the active parameter count. So usually your mixture of experts model, if you have the active parameters, your actual cost of serving these models is actually a bit more than the equivalent dense model with the same number of active parameters. Okay, here's also a really, I think, a really interesting research question: is how do you balance loads at inference time, right? So your gating layer might still decide to do unbalanced loading at inference time, which makes inference slower. What that means is that ideally you want your 8 experts, or like however many experts you have, ideally you want them to handle the same number of tokens, such that you don't get the slowest. You don't always have to wait for the slowest expert. And some nice ideas are around like mixture of depths and also dynamic loading based on scores. So some of the ideas are like if you saturate one of the experts, maybe you can try to find a neighbor of that expert to give the token to, which is not saturated, and then sort of try to slowly fill up the number, the total number of expert times token count you have. Okay. Another, I think, quite open research question is how can you compress SMoEs? And this comes from a screenshot someone took of Tim Detmers, because I really trust this man's model compression skills with my life. So Tim Detmers said he thinks we can compress a mixture of experts model to lower smaller than 4 gigabytes. So because MoE compression is quite different from dense transformer compression, because the regular transformers, they're really, really difficult to sparsify. And this is really true for like the feedforward, the MLP layers. But the MoE layers are quite different. So maybe there's something you can do with MoE layers such that your compression is much more efficient. So by compression here, I mean sparsification. So like a lot of the so sparsification, not in the sense of like choosing only top 2 experts instead of 8, but I mean a lot of the parameters might be like doing not much work, and you can like share them out. Okay, so this was said by Tim Detmers in December last year, and I don't think I've seen like much convincing work on like sparsifying MoEs to an extreme, but I really like more work going on here. Okay, now I want to talk about how to interpret mixture of expert models. So the mixture of expert models with a sparse gating layer actually provide you an incredible opportunity by giving you discrete gating signals. So deep neural networks are traditionally very, very hard to interpret, since like all the weights and activations live in very high dimensional spaces, and the attention in transformers potentially offers some interpretation opportunity, because you can look at like how much of the attention weights get assigned to which tokens, or to which tokens, but like you're essentially picking at like what is the model looking at by looking at the attention scores.
But this also quickly gets very messy as you have a lot of attention heads, and it's hard to visualize and hard to interpret. And the gating layers in SMoEs potentially tells you a bit more because it tells you like which experts is looking at which tokens. So can we make some sense out of this then? So in our paper, we try to find if there's some sort of domain specialization with these experts. So we took the validation splits of the PAL datasets, so these are represented in different colors. You can see the red is archive, the green one here is GitHub, and the sort of blue one here is field papers, the purple one is Stack Exchange. And for layers 0, 15, and 31, so these correspond to the shallowest layer, the sort of mid layer, and the deepest layer. So this is the layer 31 is the layer just before decoding. So for each of these layers, we plot how much each expert is selected. Since we have 8 experts, the sort of random selection chance is around 12.5%. And you can see that at layer 0, so this is the layer that's closest to the raw tokens, you will see that the distribution is quite uniform. It's not like very uniform, but quite. So this might be telling us that this layer is like too shallow, that it's still doing a lot of syntactical stuff, that you don't get a lot of meaningful domain specialization going on. And on the sort of the mid layer, so here is potentially where you get a lot of semantic information. You can notice that expert 3 here is doing something quite interesting, right? So because it gets selected not very often for any of the other categories, but it gets really selected quite a lot for DM mathematics, and second place is GitHub. So maybe this layer, maybe this expert 3 in layer 15 is doing something that's math and code heavy, but this is quite speculative, and we cannot really conclude much out of it. And for layer 31, I think the distribution go back to close to uniform again, although you get some spiking distributions here and there that specialize in mathematics, it seems. Or since the data set is DeepMind mathematics, is more like arithmetics. Okay. We also did some analysis on consecutive tokens. So the question to ask here is whether 2 tokens that are consecutive get assigned to the same expert. So here we have the first choice. So that means if a token is given to expert I, does the next token also get assigned to expert I, right? And we're still doing this analysis on the 3 layers, layer 0, layer 15, and layer 31, corresponding to 3 different places in the network. And the validation set is still the PAL validation split. So the random chance assignment score, random chance assignment will give you 12.5% in terms of like how many of the tokens that are assigned to expert I still get assigned to expert I. The next token also gets assigned to expert I. And we can see that at layer 0, this is slightly higher than random, but at layer 15, this is significantly higher than random, right? So it's almost double the random chance that the first choice for the gating layer will actually assign the next token to the same expert as this token. And when you go to the last layer, you'll find that this trend sort of regresses a little bit. It's still quite significantly higher than random, but it's a bit less than layer 15. We also look at like the first or second choice. So if this expert is not chosen as the best expert to route this token to, could it be the second best? So here the random chance probability is around 46%, and you can see for layer 0, we have the sort of the same pattern, right? So for layer 0, the number of times that the next token get assigned to the first or second choice for this expert is around just slightly higher than random. And for layer 15, this is really significantly higher. And then for layer 31, it sort of regresses a little bit. So I think there's certainly some sort of more detailed analysis to be done here that we can conclude out of the from these mixture of experts models. Also, we try to visualize in 3 examples, like which experts actually selected which tokens. So we have 3 examples. So the first example is actually from the GitHub code for the SMoE layer. And the second example are like simple arithmetic questions, I think from DM mathematics. And the third is from a simple multiple choice question. And this is for layer 0, layer 15, and layer 31. You can see that there doesn't seem to be much specialization, right? So here, a lot of digits get assigned to the same, so the colors represent different experts. So here, all these digits get assigned to the same expert, but that seems to be it. We don't see a lot of like very clear distinction between like which experts like which tokens, right? So that really closely relates to myth 4. That is, the myth 4 is that you want experts to specialize in domains. Let's say you have 2 experts specializing in coding. So that means they just basically, like if you have some code, they'll just handle all the tokens. Then what do the other experts do when you're coding, right? So when you want to generate a lot of code, it seems that you will only have the chance to route all your tokens to these 2 experts, and the other experts just stand there and do nothing. So you actually want all the experts to be fully engaged at all the time to maximize your inference efficiency. Language also is so complex that manually specifying these domains that experts should specialize over seems to be a simplification to me, because there might be like a lot of underlying features that the experts are actually specializing over and just not present at the high level, like the very high domain level. There's a treasure hunt. So this is why we love open source so much. So like after 24 hours of our Mixtral 8x7B model release, there's a guy on a Chinese website that just found out that there is one expert in one of the layers that's particularly crucial. So what they did was that they try to remove the ith expert from all of the layers. And here you can see what are the effects if you remove the ith expert, and on the vertical axis is the MMAU score. It seems that if you remove the 3rd expert, then everything just collapses. The MMAU score is 0.63. So this is 0.63%, not 63%. And for other experts, if you remove the ith expert, the MMAU scores drop a little bit, but not too much. And they made this meme about it. So the expert 3 seems to be doing all the work while all the experts are sort of standing around and do not much. Okay. So I think another really important research question here is, how do we interpret the mixture of expert decisions, and what are the features that they're learning? So the experts might capture features that are really different, very different concepts than what we perceive as concepts. And it might be more efficient to represent linear combinations of concepts as long as they span sort of the same subspace, right? And how do we recover that subspace, or how do we recover some of the sets that we can actually understand what are the underlying concepts that they're actually learning? Okay, so I just want to also just conclude here that a sparse mixture of experts models are leverage sparsity to gain a lot more knowledge, and you can train very good mixture of experts models to be quite efficient at inference. And expert specialization is not as straightforward as one might think, and there's just tons to do in architecture and interpretability research. And also just want to plug Mistral AI, co-founded by Arthur, Timothy, and Guillaume, and we have offices in Paris, London, San Francisco, Bay Area. It's actually currently in Palo Alto. We have 500 million in funding, and if you enjoy solving the research questions that I just mentioned, or doing open source AI, or just generally empowering people with language models, you're very welcome to join us. Thank you very much.
If any of y'all have any questions, feel free to come up and ask.
So I recently read the paper from Meta. They are using the intensive model, not this one, 28, I think, page 28.
Okay.
Yeah.
Okay.
So which is, I feel like it's the other direction, opposite way. Why you choose the sparse mixture of experts rather than the other people now? I see most of them using the intensive models, like to do some of like an edge database, like in a confined scope, you can have more knowledges in a confined scope. That's, I see the train goes to that way. For example, you go to the Egypt Museum here in, I think it's Sunnyvale somewhere, right? So you can have the ChatGPT have the local knowledges, which you cannot get it from the internet, but you can only cooperate with the museum and get it. I think the intensive model allows this kind of more domain knowledge, like going deeper. But now here you are using the sparse model with mixture of experts. To me, it's the opposite. Can you explain why? Yeah.
Sure. So if I understand the question correctly, the question is asking why are we choosing sparse mixture of experts models instead of dense models that are there's no sort of sparsity involved. So I think for edge devices, dense models have a lot of potential because for sparse mixture of experts models, although you have sparsity in inference time, so that means a token does not have to see all the parameters, but rather just a small fraction of it. You still have to load all of the experts into memory, and that might pose a huge challenge for edge devices. So your phone might not have like 200 gigabytes of memory in order to run inference like very very efficiently. But for like I guess for data centers or for people who are serving these models, it might pose a advantage in terms of inference cost because you can have very good performance divided by cost ratio.
I see. So your point is because there's not enough memory at the edge. So for the edge, it's better to use sparse model rather than densive model.
Oh, sorry. No. I meant for edge, I think it's good to use dense models.
Okay.
Because for sparse models, you still have to load everything into memory.
Yeah. So your use case is more for like closer to the center of the cloud. Is what you mean?
Yeah.
Okay, got it. Thank you.
Thank you. Does anyone else have a question they'd like to ask? Yes. Do you want to?
I have a question in regards to fine-tuning. We've been working with multiple models, so Gemini, ChatGPT, Llama, and there is a big problem of fine-tuning these models, especially on tensor on images. They're like having issues with understanding. What can you say about that?
You mean in general fine-tuning language models on visual tasks?
Yeah.
I guess that's a very broad question. What I can say about that is there's I guess for ChatGPT and Gemini, you don't really have the model weight in your hand, so you are basically relying on OpenAI or Google to do LoRa for you, right? So I guess you have less control over your fine tuning, whereas for an open source model, or I guess open weights model, you actually have weights in your hands, so you can do LoRa, you can do full fine tuning. I guess you get more control, and I guess that's in general like what I can say about like fine tuning open source models versus very closed source models. But like I guess that really highly depends. Like
exactly what happens when you're doing fine tuning really depends on your use case and your data.
Yeah, I mean, I'm sorry, I was a little broad. So when we start transferring them into a large data sets, let's say like 10,000 images or 5,000 images. So, and you have to transfer them into textual format because none of these models are actually designed to be fine-tuned on images. They don't understand it. So is this something you see in development in open source models?
So by translating these images into text, do you mean like OCR, or
Yeah,
is that
into
something?
digital format, into textual format. So they do understand them in as an image if you upload them into like text line, right? Like you go to ChatGPT, but when you start feeding them through APIs, you need to transfer them. So then it becomes a problem. Like, is there any way to overcome this issue with open source models?
I guess I'm not. I guess I'm not entirely sure what the root cause of this problem is, but I think I'm sure that with open source models you can actually, well, you can see like what the weights are doing, right? So you can actually tell what are like you have more control of the weights basically. So I think the open weights models definitely pose an advantage here.
Thank you for the question. Does anyone else have any other questions in person?
Yeah, I guess I was curious, like where you think the improvements of mixture of experts are like coming from. Like I've heard that you can like put different experts or different like feedforward networks on different GPUs, and that like allows it to be more parallel and like speed things up from like a compute perspective. Or is it like more the sparsity itself that is like giving these improvements? I guess, is there any insight on that?
I guess there are two dimensions to this, right? So in terms of improvement, the one dimension is performance. As I said, the mixture of experts models have these MoE MLP layers. So imagine your original MLP layers, and then you make it 8 times wider. You will be able to store a lot more knowledge into these layers because, well, you have more parameter counts. So that's, I guess, on the performance dimension, that you can actually store a lot more knowledge into these models. And on the performance, and the other dimension is the inference efficiency dimension, right? So definitely go read the switch transformer paper where they discuss the okay, I guess that's training efficiency, but they really discussed in quite a lot of details about data parallelism, model parallelism, and expert parallelism, and how they affect the efficiency. What's the communication cost there? What's the best way to train our models? And for these sparse mixture of experts models, since you only select 13 billion parameters for each token at inference time, you are actually trying to select the most relevant parameters for each token. So that can make inference quite a lot more efficient. I hope that answered your question.
Yeah, no, that definitely did. I guess I was also wondering, like, if you've seen like the mixture of depths paper, and like that as like a way of sparsity. Do you have any thoughts on that?
Yeah, I think sparsity helps when you can do like adaptive computation. So the mixture of depths model is like the best example of the adaptive computation, which means for different tokens, for predicting different tokens, you want first different parameters to engage. So in the mixture of depths paper, they selected different number of parameters to engage in calculating each token. And in our paper, we selected different, like the same number of parameters, but different experts. So it's the difference is I guess quantity versus quality. But there are like two different dimensions you can optimize over. You definitely want to select the most relevant parameters and as few parameters as possible for decoding a token.
Yeah, I think that was all my questions.
Perfect. Thank you. We'll take one more in-person question if any of you all have anything. If not, we can turn it to the online questions. Yes.
Hey, Albert, thanks for the talk. Just one in the earlier, like beginning of the presentation, you mentioned like routing and communication costs. And I was wondering if you could talk about like how that scales, relative to the number of experts you have and parameters.
Oh yeah, sure. So that depends on like the number of experts you have, and also depends on like how large each expert is. So that sort of can change the way you do parallelism. So we know that communication is really expensive when you need to go from one GPU to another, and it's more expensive if you want to go from one node to another. And if you have a huge ton of experts that will not fit into just one node, then you really incur a huge, quite a big communication cost. And like how to scale beyond that is I guess is a very open scientific questions. But like essentially the communication costs you incur is roughly proportional to the number of token routing first between GPUs and then between nodes.
Thank you.
Thank you for all the questions. We'll have Stephen introduce some of the questions that were submitted by the people joining us on Zoom.
Hey, yep. Can you hear me?
Yep.
Hey, thanks for the great talk.
Thanks.
All right, so we have some questions through Zoom and Slido. I'm gonna pick and choose some of them, starting with some Zoom questions maybe. So we have a question here about any comments on why potentially Llama 3 is not using a mixture of experts. A lot of people suspected they might after Mistral success. I don't know if you would know anything about that, but
Yeah, I don't know. Just ask the Llama people. Sorry.
right. Let me see. Here's a question. Do you foresee mixture of experts techniques being incorporated into the other large foundation models, or will it remain a subset of models that are best for certain use cases?
Oh, certainly. So I think as my answer to the first like in-person question was, for edge devices, you probably want to stick with dense models because of the memory constraints. And for mixture of experts models, you really gain a lot in efficiency if you can serve it at scale. So if you have high batch sizes, you will potentially be doing better in terms of throughput than the dense models. So yeah, it definitely depends on depends on your use case. Usually the larger the scale, the better I guess the more the benefit of the mixture of experts model shine. And well, it's speculated that GPT-4 is a mixture of experts model, if you haven't heard already.
Can mixture of experts models outperform domain-specific models at their respective tasks with experts?
So, well, first, usually models that have been trained for particular domains are really hard to beat. And I think that's where the purpose of continuous pre-training and fine-tuning comes in. So if you let's say you first pre-train a general text model, and then you want to adapt it to the medical domain. So you grab a lot of medical data, and then you continuous pre-train or you fine-tune on that. That model is going to be really hard to beat. And I think the mixture of experts model, the experts don't really, at least in our case here, the experts don't really focus on like traditional like domains as we know it. We don't have a medical expert, we don't have a coding expert. Rather, they just try to extend. They have concepts encoded in a very non-interpretable way. So I wouldn't say that just taking one mixture of experts model would just outperform all the other like domain-focused models.
All right, that makes sense. Here's a question. Has there been any study on whether the MoE layers should be both at the early layers and deep layers? For old neural network ensemble methods, late fusion tends to work better than early fusion.
So, okay, I think that's a really great question because I think from the inception, from the neural network, we are trying to adopt this. We're trying to we sort of have this tradition of having layers that look exactly the same as at each other. So you have, so that you can try to focus on just designing this layer to be as perfect as possible, and then you can just copy paste that a couple of times. But I think I've recently seen a paper. Sorry, I don't remember the name, but I think they're just trying to put layers in random orders. So sometimes it can be attention first, sometimes it can be MoE first, and they can have also some other quite wacky layers. But I think that performs quite well. It's unclear to me like why that is. It could be just chance. But I guess if you want to design a generally really performant model, it's really safe to have the same architecture for every layer. So yeah, so I guess that's the safest choice. You can also do some sort of neural architecture search in order to optimize your optimize your architecture. But which is a much more principled approach than sort of guessing that this layer might work better.
All right. Thanks for the answer. Asking, could you talk a bit more about how the 8 experts are built? Are they just fine-tuned on different data sets?
So they are trained on roughly the same data sets. But I'm not sure if I can say more than that. But yeah, sorry.
All right, and here's a question. Some work has suggested that learning to route doesn't perform any better than simply using, for example, a random mapping of inputs to experts. Do you have any thoughts?
I think that I would definitely need to see the paper first, but I wouldn't be too surprised if that's the case. I mean, I would still be surprised, but not like extremely surprised, because if you think about MoEfying the MLP layers as augmenting the knowledge capacity, then it seems that you can potentially just do that in a very brute force way and just randomly mapping the tokens to random layer to random experts. I would still think that the gating has the advantage of of being able to choose experts more intelligently than just randomly. So yeah, I don't know that paper, but I would love to see it.
Someone was asking, could you speak a bit about the general development process from your perspective for this model? What aspects, design choices, hyperparameters, and so forth did you try that did not work before arriving at this specific architecture?
So we know, so for this particular architecture, the Mixture of Experts architecture, we kind of know that it will work because they're having a lot of successful papers beforehand. In terms of like what sort of things you need to consider, I think one really good practice, I guess, for an AI company instead of as a single developer, is to always consider, like you always want to take inference needs. You want to think about inference needs before you design the architecture for a model. You don't want to. So, for example, you don't want to have a model that sort of just slightly exceeds like what a single 80 gigabyte H100 can contain, and then you basically lose a lot of efficiency from just like being like the overhead being just a little bit more than 80 gigabytes. So I think in terms of design, before training the model, you definitely want to consider how to infer with this model. And in terms of the hyperparameters, you definitely want to do some sort of scaling law before you like some sort of scaling law, I guess, search and analysis before you train a model to make sure that your model is served at the best performance cost ratio. So yeah, that's it.
Great. Speaking of GPU memory, someone is asking, what is the inference runtime GPU memory footprint for the 7B model versus the 8 by 7B? It would be great to understand this for specific applications, especially if Mistral has the potential to run on edge devices with sufficient GPU VRAM.
Sorry, I don't think I got the last part of the question. So edge devices and GPU.
Oh no, they're just asking what is the approximate inference runtime of in terms of GPU memory footprint for the 7B model versus the 8 by 7B.
Okay, I see. So if you do like if you do very naive if you do it very straightforwardly, that you load for the 8 times 7B to load all the experts in, and then the experts always stay in GPU memory, then your then the difference between the 8 times 7B and the 7B will be the same as the ratio between 46.7 to 7. That's the memory requirement. But at inference time, since the mixture of experts model only has 13B active parameters, so each token gets to see much fewer parameters than there are in the memory. And you can do some interesting things like I think CPU. I kind of forgot the name for it, but you can keep some of the experts in CPU and then only load them when you need them. So I think that's something you can do as well. But then you also lose some efficiency because you need to constantly transfer parameters from CPU to GPU and vice versa.
Right, that makes sense. Speaking of parameters, someone asked, do you have a rough rule of thumb for how to approximate how capable an MOE model would be in terms of equivalent dense parameters? For example, I've heard that calculating the geometric mean of active parameters to total parameters is a good way to do this, which would mean that 13 billion active parameters with 47 billion total parameters would be equivalent to a 22 billion parameters dense model. I'm wondering how accurate that would be.
So I think that's a good rule of thumb. Although that definitely depends on like how well you train these models, and how many tokens do you put through them, and how good are those tokens. If all other things being equal, I think that's a very good rule of thumb.
All right, great. And I'm just looking at some of the upvoted Slido questions. Someone asked, for the treasure hunted expert, was there a reverse experiment of removing all experts except number 3?
Oh, that's a great question. I think, yeah, if you can figure that out, I'll be really I'll be all ears. I'll be really happy to hear that. So then you're just trying to, I guess you're trying to trim the 8 times 7B back into a 7B, which might be an interesting experiment to do.
Right. Someone asked, what is your intuition about why the 8 by 7B is significantly better at reasoning compared to the 7B? Are they learning better internal algorithms?
That could be the case, although I think that's very speculative. I think for a lot of these benchmarks, for example, even for the math benchmark, the what you do, what sort of things count as knowledge and what sort of things count as reasoning is quite ambiguous. For example, if you're doing a math task and you can reason to get something out, or you can just recall, oh, here's a lemma, and I can just use that. And so I think there's like a high ambiguity between what sort of things count as knowledge and what sort of things counts as reasoning. So for this particular example, the 8 times 7B definitely gains a lot more in knowledge. But does the gaining knowledge also induce some sort of change in its reasoning capability? I don't know. But I think that's just like whatever I can say about it is like highly speculative. But I'll say the benchmarks themselves are also very ambiguous. So I think it's worth finding out what exactly it's doing.
Great. Another question about GPU memory. Someone's saying in production, we're constantly bounded by GPU memory instead of compute. Will Mixture of Experts make it more challenging to serve? any extra cost besides communication overhead?
So in terms of cost, I think communication, yeah. So when you say you're bounded by GPU memory, I assume that it's like comparing the 8x7B to a 7B. Then yes, if you need to load all the experts into the GPU memory, then yeah, you're gonna consume. You're gonna use a lot more. So the benefit or the advantage of the 8x7B over the 7B is that or let's say over an equivalent dense models with similar active parameter count, is that at high batch size you'll get more throughput because you'll get different experts handling the tokens at the same time. So I'd say yes, mixture of experts model definitely gives you a little bit more trouble in terms of serving, but if you have high volume, it's definitely worth it because you get much more efficient in processing these tokens.
Okay, great. Here, I'll ask a few more since we do have some extra time. But do let me know when you might need to leave.
Sure.
So someone is asking specifically about the architecture. They want you to clarify, does each layer include attention, routing, and experts? Or layers of attention, then routing, then experts?
Okay. Let me try to find it. Yes. So the architecture of Mixtral 8x7B is exactly the same as Mistral 7B, as I've shown here. So in Mistral 7B, you first do for each of the input, you do normalization, you do attention, residual, norm, MLP, residual. So it's attention followed by MLP. Okay, and the only difference is in the MLP layer here. So so after the attention layer and after the attention residual, instead of doing MLP, you do an MoE MLP here. So here, instead of just using one or a couple one matrix to process these hidden this latent representation, you use 8 experts. Well, you choose 2 out of 8 experts to process that.
Right, that makes sense. All right, let's see. Give me a sec. Last, MoE introduces extra load balancing losses and loss function discontinuity. Did you run into any difficulties while training due to these complications?
Yeah, that's a really great question. So I think to try to clarify the question, my understanding is that when you're training mixture of experts models, you definitely want each of your expert to be quite balanced in the sense that they handle a similar amount of tokens, such that you're not like, I guess I was waiting for the slowest expert or the expert that handles the most. So yes, you definitely need to do something to make the load balance a bit better in training. But we didn't run into any big troubles during training this model.
And here's a question about RAG. Curious to hear when an MoE approach would be preferred to a RAG approach in a given domain, pros and cons, etc.
I think these are orthogonal, so you can use an MoE model to do RAG. So I don't see why there should be a conflict between the two. Yeah, so like you can do dense model no RAG, dense model RAG, MoE no RAG, MoE RAG.
Right. And someone asked, can you potentially swap out one expert and insert a domain-specific expert that wasn't trained on the same training data set, like a customizable or modular MoE?
I see. I think that's possible, given that you also you also need to so after you swap out one of the experts and replace it with a domain specific expert. But after you do the swapping, you definitely need to train this model a bit more, such that the gating layers know how to route the. Let's you have a medical expert swapped in. You need to train your gating layers a little bit, such that it knows how to handle medical situations, and to basically treat this replaced expert quite differently. So I think it's totally possible and very exciting research direction. There being quite interesting research done on like merging and swapping and Franken-merge these models. So I think that's something very exciting. I'm looking forward to it.
Okay, great. I'll ask 2 more Zoom questions and that'll be it. So someone asked, during training, is Mixture of Experts less computationally intensive since the gradients would always be 7B? How do the gradients back propagate through the routing head?
So if I go to the routing layer, you will see that the top so all the operations here are differentiable. So there's no I guess like discrete operations such that the gradient just stops there. So this thing is entirely like end-to-end differentiable. Sorry, what's the first part of the question again?
They're asking if training MOEs is less computationally intensive.
So the cost of training MOEs is roughly proportional to the number of active parameters you have. And so it's roughly equivalent to training a 13B. But you incur some extra communication cost.
Okay, great. Last question. Let's talk about even bigger MOE models, even if we're moving away from the Pareto frontier, like those 8x22, 8x30, or even 8x100 plus billion parameter models. Do you see any further serving challenges when one GPU cannot even hold a full expert after heavy quantization?
I see. Yes, so I think if you have one GPU, I think I would go for a dense model or a heavily quantized mixture of experts model. And about like what you said about like having more modular experts, like having 128 experts, I think that's something super exciting because that basically allows you to specialize your basically allows your experts to specialize a bit more. And that's always exciting. You can always reduce the number of you can always make the experts specialize better, and you can pick, but basically giving your gating layers more power to choose like which experts are the best for this token. I think for serving purposes, that will definitely make things very, very hard. Even after having quantization, if you have 128 experts, then and potentially we're talking about having the model in multiple nodes that will make both make the implementation harder and also the communication cost higher. So that's something you probably want to leave to a model provider through API instead of like serving it yourself. But I think for like mixture of experts model, Mixtral 8x7B is definitely, after quantization, is definitely very very doable almost as on a single GPU.
All right, great. Thanks for answering a bunch of questions from very curious folks. So thanks again, Albert, for the amazing talk and the time today.